Welcome to the third week of the course. In this module, we finally descend from abstractions to the solid ground and discover some algorithms. And we start with the first algorithm ever designed for a quantum computer, the algorithm for solving the Deutsch problem. Actually, this first algorithm, presented by David Deutsch in 1985, was not the main topic of his paper. The main topic was the mathematical model of quantum computing, which we learned on the previous week. And the algorithm was just an illustration for this mathematical model. So thanks to this man, we now have this good mathematical abstraction, which allows us to design quantum algorithms without any extensive knowledge in quantum mechanics. And I placed here on the slide some covers of his popular books. In fact, he has more, but these two are very popular here in Russia, and they are the only I have read, so I can personally recommend them, and so I do. Here is the plan of our third week. And we start, as you may have noticed, with Deutsch's problem. Then we are going to make a quantum computer with our own hands. This quantum computer you can see in the picture here. And then we are going to solve Deutsch's problem on this real quantum computer. And after that, we will learn some basic algorithms. So let's start learning. Deutsch's problem is about a function which maps one bit to one bit. And there are only four such functions. We can easily name them. So f of x equals 0 and f of x equals 1. These two are constants. And the balanced functions, which have the equal amount of ones and zeros in their image. This f of x equals to x, and f of x equals to not x. I call them balanced. And the function itself is implemented as a black box. This metaphor means that we can't see how the function is implemented. We don't know how it works, we only can query it as an oracle. So we can give it an input, 1 or 0, and read the output. So it's black box here. And unluckily for us, this particular black box is very slow. One query takes 24 hours. And the question is, which type of the function sits here in the box? Is it constant or is it a balanced function? So how much time do we need to answer this question? And in classical case, it appears that we still have to query this oracle twice to give it 0 and 1 and to see what it returns. After that, we will know exactly which of these functions sits there. And this is useless information for us. We needed only type, and we paid for this useless information with our time, with extra hours. And in classical case, there is no hope to solve this problem faster, but in quantum case, we have an algorithm which does it. As we learned before, all quantum operations are performed by unitary operators, and the quantum data is represented to us by vectors in a Hilbert space, and we have a function which maps one bit to one bit here. So we might expect for a quantum substitute for this function, we'll call it UF. You might expect that it maps one qubit to one qubit, for example, like this. Is it fine? No, because if function f is a constant, 0, for example, then this operator glues together different basis vectors, so it will map 0 to 0, and it will map 1 to 0, and thus it is not unitary. So this operator does not work for us, it's not unitary, and to fix this we need to add some extra qubits, like this. We add this second extra qubit, and we map it like this. Okay, now these two vectors, 0, 0, and 1, 0, are not glued together because they still map to different vectors. And it seems that we solved the problem, but not completely, because this unitary operator UF must be defined on the whole space. That means on all basis vectors. So we need to define how it works on these states. And we can define it like this. To distinguish these vectors from these vectors. And the operator defined like this maps orthonormal basis to orthonormal basis. So let it be the definition of our quantum oracle, which works like this. And this plus here is a XOR operation. Having quantum oracle defined like this, we obtain another useful and interesting feature. If we apply our oracle to this type of states, where in the last qubit we have this Adamar minus, let's see what we get. So this operator is linear, and we can write like this: x0 minus x1. Now let's recall how this operator works. U x f x minus u x 1 plus f of x. And now, sorry, no u here anymore. Now, if f of x equals to 0, we have x 0 minus x 1, which is our initial state. X 0, minus 1. And if f of x equals to 1, then we have x 1 minus 0. So it is minus our initial state. And we can write it like this. So we can see that this operator UF on this state does not really change the state. It only adds this coefficient here, minus 1, if f of x equals to 1.